Welcome, everyone, to today's Explainer. We're going to dive into a topic today that honestly feels like it was ripped straight out of a sci-fi novel. But the crazy thing is, it's actually happening in laboratories right now. We're talking about the biological computing revolution. Now, hooking living, breathing biology right into our cold, hard computer technology might sound totally bizarre. But as we're about to see, our entire digital future might literally depend on it. To really grasp why we need such a massive radical shift, you just have to think about this astronomical number, 175 zettabytes. That is the projected volume of all global data by the year 2025. I mean, we are generating data at a pace that is completely unprecedented, and it's leading us straight into a massive data storage and energy crisis. Our current hardware simply cannot keep up with this explosion of information. We absolutely need a new way to process and store all of this. And the solution? Well, it might just be growing in a petri dish.
So here's our roadmap for today. We're going to cover 1. The silicon crisis, 2. Biocomputing, 3. DNA data storage, 4. Current hurdles, and finally, 5. The ethical frontier.
All right, starting right off with Section 1, the silicon crisis, and how we are hitting a physical wall.
For decades, we've basically relied on silicon microchips to power our world, but we're quite literally hitting a wall here. First off, the energy demand is just staggering. Cloud data centers already chew up roughly 1% of the entire globe's electricity. And with the massive surge of artificial intelligence, this is only getting worse. Remember Google's AlphaGo? Training those massive AI models requires nonstop processing and unbelievable amounts of power. But here's the real physical limit we're facing. Moore's Law, that old idea that computer chips will just continually get smaller and faster, is dying. Our most advanced printers are making transistors as small as 2 nanometers. To put that in perspective for you, a single atom is about 0.5 to 1 nanometer. We physically cannot shrink these chips much further. Add in the von Neumann bottleneck, which is that massive inefficiency of constantly shuttling data back and forth between a computer's memory and its processor, and it becomes super clear that silicon has basically taken us as far as it can.
Which brings us to Section 2, biocomputing, or the idea of the living processor.
If silicon has reached its limit, we need a sledgehammer to break through that technological barrier. And that sledgehammer is biology. Biocomputing is any form of computing done on a system that combines traditional computer technology with biological components. Now, at first glance, this seems like a total clash of two different worlds, right? You've got the messy, wet lab of biology versus the very structured, metallic world of computing. But pioneering companies like this Swiss startup named Final Spark are already bridging this divide. They are successfully connecting living brain cells to electrical arrays to process information.
This brilliantly illustrates the whole David versus Goliath difference between our absolute best silicon tech and nature's technology. Think about the Frontier supercomputer, one of the most powerful on the planet. It processes at about 1.1 exaflops. But to do that, it requires 21 million watts of power and weighs 8,000 pounds. Now, compare that to the human brain. It operates at roughly that exact same 1 exaflop of processing power, but it does it on just 20 watts of energy and weighs a mere 3 pounds. 20 watts. The biological brain is 1,000,000 times more energy efficient, and it naturally fuses data storage and processing into one single unit, which completely bypasses that von Neumann bottleneck we just talked about.
So how does this actually build into a functional living computer? Well, a company called Cortical Labs created something they dubbed the dish brain. They grew about 800,000 brain cells in a lab dish, and quite literally taught them to play the classic 1970s arcade game, Pong. It's wild. Here's how they did it. First, they delivered sensory input from the game to the cells using electrical impulses. Second, because brains are just natural sense-making machines, the neurons rapidly reorganize themselves to understand this new flow of information. And third, the cells fired electrical signals back out through a motor region to actually move the paddle in the digital game. But think about it. How do you motivate a dish of cells to actually care about winning a game of Pong? I mean, you can't exactly offer them a trophy, right? Scientists pulled this off using something called the free energy principle. This is a framework that suggests living systems naturally want to minimize surprise and chaos in order to conserve their energy. So the researchers set up a biological reward system. When the cells successfully hit the Pong ball, they were rewarded with a nice, predictable burst of electricity. But if they missed, the cells were reprimanded with chaotic, unpredictable white noise. And to avoid that chaos, the cells learned to play the game. Incredibly, they actually learned faster in terms of rallies than a digital AI. And this isn't just some abstract theory locked away in an academic paper somewhere. This is an active, commercially viable frontier right now. Final Spark, that Swiss startup we mentioned earlier, currently leases virtual access to their in vitro biocomputers. For a setup fee and a $500 monthly subscription, research institutions can just log in remotely and run computational experiments on living neuronal tissue 24/7. As they put it, this technology is truly scalable because it effortlessly expands through natural cellular growth.
All right, moving on to Section 3, DNA as the ultimate hard drive.
So living processors fix our energy and processing limits. But what about that 175 zettabyte data shortage we started with? Well, let's talk about the sheer durability of DNA. Our current silicon and magnetic storage drives, like the ones sitting inside your laptop right now, have a lifespan of maybe 50 years before they start to physically degrade. It's exactly why we constantly have to migrate our data to new drives. DNA, on the other hand, it can last for millennia. In fact, scientists recently extracted entirely readable DNA from the fossilized bone of a bear that lived 300,000 years ago. As an archival medium, it is virtually indestructible if you keep it in the right conditions. What's honestly mind-blowing is how simple the translation is between our digital world and the biological one. Computers read data in binary, just zeros and ones. DNA stores genetic information using 4 chemical bases: adenine, thymine, cytosine, and guanine. By simply mapping binary pairs to these bases, like say 00 becomes A, 01 becomes T, we can actually encode digital files directly into genetic code. And the density is just unbelievable. Just 1 single gram of DNA can hold 455 exabytes of data. That basically means all the data in the entire world could theoretically fit in a space the size of a shoebox. Let's walk through how this biological zip file actually works in the real world. You start with your digital data input, say a text file or a photo. Next, you go through data encoding, translating those digital ones and zeros into a sequence of A's, T's, C's, and G's. Then comes DNA synthesis, where specialized machines chemically print out the actual physical strands of DNA based on that exact code. That physical DNA is then safely preserved in storage. When you want to watch that video or read that file again later, you go to data retrieval, which extracts the DNA, and finally, data decoding, translating it perfectly back into your original digital output. To get that data back out during the retrieval phase, we rely on established biological hardware through a process called sequencing by synthesis, which was popularized by companies like Illumina. Just like a medical lab sequences a human genome to look for traits, this hardware takes our synthesized DNA fragments, generates clusters, and uses fluorescent detection to read the biological alphabet back out. It essentially scans the genetic material and translates it perfectly back into the digital sequence that you originally saved.
Okay, Section 4, the hurdles in biological computing.
Now, I know this all sounds incredibly perfect, right? Like magic? But let's ground this explainer with the realistic hurdles we're currently facing before this replaces the tech sitting in your home. The most staggering roadblock right now is purely financial. Archiving 1 single terabyte of data on standard magnetic tape costs about $15. Synthesizing that exact same terabyte of data into DNA, that currently costs around $800 million. So while DNA storage is incredibly dense and durable, the chemical synthesis required to actually write the data is excruciatingly slow and massively expensive right now. So yeah, we have a lot of optimizing left to do. Just summarizing the other major hurdles here. On the processing side, current biochips are significantly slower than silicon chips, and they are highly sensitive. Like a simple change in the room's environment can actually impact the accuracy of a biochip's calculations. Plus, quantum computing is rapidly developing as a major competitor to solve the whole silicon crisis. On the storage side, aside from that $800 million price tag, DNA synthesis is prone to chemical errors. And while DNA can absolutely last thousands of years safely tucked inside a fossilized bone, in a lab, if it's exposed to moisture or oxygen, it is highly vulnerable to degradation through a process called hydrolysis.
Which brings us to our final section, the ethical frontier.
We absolutely have to address the elephant in the room here. As we merge human biology with commercial technology, we're entering a very murky sci-fi reality. The primary ethical debate centers around organoid sentience. When we grow hundreds of thousands of human brain cells in a dish to process data, can they develop consciousness? Can they actually feel pain?
Right now, the scientific community is heavily divided on this. Some prominent physicists argue that consciousness is a deeply complex phenomenon that simply cannot be manufactured artificially in a petri dish. But on the flip side, other researchers point out that these neurons are actively responding to external stimuli and learning from their environment to avoid chaotic noise, which some argue could very well be a foundational indicator of sentience. Because we still don't fully understand exactly how the human brain works, it is currently impossible to definitively prove either side.
Which leaves us with this final, really profound question to think about. If our computers become biological and human brain cells are leased out as commercial processors, where exactly is the line between a machine and a living being? The potential of biocomputing to solve our energy and data crises is absolutely undeniable. It really could revolutionize our entire world. But as we step into this new era, we aren't just pushing the boundaries of technology, we are fundamentally challenging our very definition of life and intelligence. Thank you so much for joining me on this explainer, and I really hope this leaves you incredibly curious about the future we're building.